Hello, what I'm going to do is go through some inverse stuff from linear and quadratic functions. So what we'll be doing is graphing inverses, regular equations, basically flipping their coordinates, getting the inverses. And then we'll do that for quadratic functions, then linear functions. And then we'll determine the inverses of all the questions that we did from the first part, and then verify them using composition. So I'll get started right away with the table of value problems. So what I'm going to do is take these values for x and substitute them into my equation. So if I take -4 and square it, I get 16. And if I divide by 2, that's 8. And 8 minus 1 would give me 7. Take the -2 and square it, that's 4. 4 divided by 2 is 2. 2 minus 1 is 1. If I take my 0 and I substitute it in, I'll get 0 squared divided by 2, which is 0. Subtract 1, -1. And then these two values are going to follow basically my pattern of a quadratic, which means that 2 would give me the same y value as -2, and 4 would give me the same as -4. So what I'm going to do is plot those. So I'm going to go to the left 4 and up 7, go to the left 2 and up 1, and then 0, -1. And then basically the reflection on the other side. So go to +2, +1, and then +4, +7. So what it's going to do is give me a curve that's going to look something like this. And I'll throw some arrows on there. And then basically in order to get the inverse graph, I'm just going to interchange my x and y columns here. So my x values would be 7, 1, -1, 1, and 7. And then my y values would be my -4, -2, 0, 2, and 4. So then I'll plot these. So I'm going to go over 7 and then down 4. Go to over 1 and down 2. I'm going to go -1, 0, +1, +2, and then 7, 4. So all the way over 7 and up 4. And I'm going to draw in that curve. So the red curve represents my inverse function, and then the blue curve represents my regular function. And it should look like a reflection then over this purple line that I'm drawing in. So then the blue curve is my f of x, the red curve is my f inverse of x, so the inverse function, and then again it's just a giant symmetric function over the line y equals x. So I'm going to do another quadratic that's in a different form. So this one was in standard form. I'm going to do one that is in vertex form. So I have a different table of values here. If I take the -5, I'm going to substitute that in first. I'm going to take -5 plus 3, which is -2, and then square that value so it becomes a +4, and then I'm going to tack on this negative sign. So I really have -4 plus 2, which is -2. And I'll kind of recap that process again. I'm going to take the -4 here, add 3, which gives me -1, then square it so it becomes +1, but then I'm going to throw on this negative sign. So it's going to become -1 plus 2, which is 1. Take the -3, that's going to go inside here and basically cancel all that out, and I'm going to be left with a +2. And then if I take the -2, the same thing is going to happen here, where I'm going to end up with a y value of 1 and then another y value of -2. So I'm going to graph this one. So I'm going to go over 5 and then down 2. I'm going to go, oops, sorry, it's -5, -2, my bad. So to the left 5 and then down 2, and then go to -4, 1. Go to -3, 2, -2, +1, and then -1, -2. So the negative sign is what turns this parabola going basically upside down. Oops. And then same thing on the other side. So what I'm going to do then is just flip-flop the points again to get my inverse function. So this function was f of x. And I'm going to interchange my coordinates, so take my -2, my 1, 2, 1, and -2. And then take those x values that now become y values. And then we're going to plot these points. So I'm going to go -2, -5, so that's left 2, and that is down 5. So yeah, 1, 2, 3, 4, 5, okay, cool. And then 1, -4, so that's over 1 and down 1, 2, 3, 4. And then I have 2, -3, so over 2 and down 3. 1, -2, and then -2, -1. Oops, that was definitely at -1, -1. Okay, -2, -1, so right here. And then this inverse function is going to turn to the left then. So because I had that negative before, which turned my blue curve down, the negative is going to make this red curve, so my inverse function basically turn to the left. So those are my two quadratic ones. I'm going to now do a linear one. Notice I don't have a table of values here. So with the linear equations, I'm going to graph them in slope-intercept form, which is y equals mx plus b. And what I'm going to do is identify that my slope is 1/4 and my y-intercept is -3. So I'm going to start this at -3 and put a point here, and then go up 1 and to the right 4, and I can also go down 1 and to the left 4, and both those points are going to be on that same line. So this is going to work basically the same way, except I'm going to have to write out these coordinates. So this coordinate here, this point here, and this one here. So I'll start with my y-intercept, which was at the point 0, -3. And then this coordinate over here was at 4, -2. And then the point to the left is at -4, -4. So all that I have to do then to get my inverse points is flip-flop those. So the -4 and -4 is going to stay the same. This one is going to become -2, +4. And this will be -3, 0. So these 3 points are going to now make a line. Here's my -3, 0. I have my -2, +4. And then I also had the one that was down here already, the -4, -4. And then I can just draw in my line going through those. And this is going to represent my inverse graph, which even though it's linear, it's still going to look like it's a reflection over this line, y equals x. And then one more linear one. So with this problem, this is not in slope-intercept form. I'm going to get it into slope-intercept form by first subtracting 2x on both sides and get 3y equals -2x minus 6. And then I'm going to divide everything by 3. So this is going to isolate the y variable and get y equals -2/3x minus 2. And what I'm going to do is identify again, I have a slope here of -2/3 and a y-intercept of -2. So I'll start with the y-intercept of -2, and I'm going to go ahead and just write that coordinate over here. So that is at 0, -2, and then move in this direction of my rise over run, down 2 and to the right 3, and then I can also, if I wanted to, go up 2 and to the left 3. So I'm going to mark off what those coordinates are. So I have this one to the left, which is at -3, 0. And then I have this coordinate down here, which is at 3, -4. So then my inverse coordinates would just be a flip-flop of those 3. So all I'm going to do is change those 3 points. So I have -2, 0. I have 0, -3, and then -4, +3. So I'm going to now plot those points. -2, 0 is here, 0, -3 down here, and then -4, +3, which is up here. And they look like they all belong to the same straight line, and that's what we end up with. So again, the quick check, basically looking if it looks like it would flip over or reflect over that purple line, which it does. So that's the graphing of the quadratic and linear functions. Now I'm going to determine the inverse of each of those functions and verify using composition. So what that means I'm going to first do is switch my f of x to a y equals x squared over 2 minus 1. And then by definition, since inverse function is basically a reflection over this purple line y equals x, I'm going to switch my x and y values. And then what I want to do is isolate the y. So we want to get the y all by itself. The first thing I'm going to do is add 1 to both sides. And that's going to give me this. And then I'm going to multiply both sides by 2. So I'm going to bring over this 2 by multiplying. And that's going to, if I throw this left side in parentheses, I'm going to have 2 times x plus 1. And on the right side, I have y squared. I'm going to take that a step further, and I'm actually going to distribute that. And this is what I end up with. And then lastly, what I'm going to want to do to get the y by itself, since y is being squared, I need to do the inverse of that, which would be square rooting both sides. So the square root and the square will cancel each other out. Y will be by itself. I am, however, going to throw a plus minus in front of the radical sign. So this is my inverse function, and then at the very end I'm going to switch it to say f inverse of x equals plus minus the square root of 2x plus 2. So I have my main function up here, f of x, and my inverse function here, which is f inverse of x. And what I'm going to do is a composition f of f inverse of x, which what I'm hoping is going to happen is these two things, and this is if I do it correctly, or if I did it correctly, the two functions should basically cancel each other out, and I should be left with just x. So the inverse functions will cancel each other. How I'm going to do that is take my inverse equation that we solve for and substitute it in for my function for x. So f of f inverse of x equals, and I'm going to basically rewrite that top function, except I left myself a little space inside the parentheses. And inside that space that I have, I'm going to put our new function, which is the square root of 2x plus 2. So now what I want to do is show you step by step how this is going to cancel out. The first thing that's going to cancel here is my square with the square root, since those are inverses of each other. And then what I'm going to really end up with are these 2's that are going to cancel. So if I divide both of these values by 2, basically, my 2x divided by 2 is just x. The 2 divided by 2 is a 1. And then I'm going to bring down my minus 1. So basically these 3 2's are what kind of canceled out just by division. And then x plus 1 minus 1. These are addition and subtraction, so those are inverses, and I'm left with just x. And that's what we really wanted, was for our composition to come out as just x, since the functions basically undid each other. Next one, what I'm going to do with this, another quadratic, start off the same way. We're going to take y equals negative x plus 3 squared plus 2. I'm going to first switch my x and y. And then we're going to try to isolate the y. So the first thing that I'm going to do on both sides is subtract my 2, and that's going to get rid of that. And now I cannot square root this yet. What I'd want to do is get rid of this negative, and I'm going to do so by dividing both sides by negative 1. So what I'm really going to do is apply that to each of these values where my cursor is. If I take the x divided by negative 1, I have negative x. And negative 2 divided by negative 1 is positive 2. And what that's going to do is free up this right-hand side of being negative. And now I have my square root, which is going to cancel out my square. So what I have is plus minus the square root of negative x plus 2, which is equal to y plus 3. So now I got the y almost by itself. My last step is to subtract the 3 on both sides. So y is equal to plus minus the square root of negative x plus 2, and then minus 3. So the last thing, just to change the y equals to an f inverse of x, and then bring my function down. So this is my inverse, and we are going to do the verification again, which is to take my inverse function that we just got and substitute it in for my variable x from my original function. So I'm going to write this out as f of f inverse of x, oops, there's my little minus 1, and that is equal to, so negative, and then in for the x, I'm going to substitute my function, which is negative x plus 2 minus 3. And notice that's just in for this x value. So now what I'm going to do then is bring down my plus 3. And then that is squared plus 2. So I'll let you take a minute and just really take a look. I dropped my function inside this this inner parentheses here. So this is my inverse function that's depicted right above, and then I substituted that in for this x value. Everything else is just brought straight down, and now we can start canceling things out. The first thing that is going to cancel are going to be these 3's here. So then I'm going to rewrite this by bringing down the negative, and then bringing down my radical x plus 2. Sorry. Let me rewrite that. That is the radical of negative x plus 2, and then that is squared plus 2. So the next thing that is going to cancel out then is going to be my square and my square root. So I have a negative sign on the outside of my negative x plus 2, and then plus another 2. So you might be thinking the 2's are going to add together. However, I'm going to have to take this negative, the negative 1 on the outside, and distribute that through. So that's the next thing I'll do. and a negative 1 times a negative x is a positive x. Negative 1 times 2 is negative 2. And then I'll bring down this positive 2. So what ends up happening then is my 2's would cancel out, and I'm going to be left with x. Alright, on to the linear equations then. So this one is written in slope-intercept form. I'm going to go about it the same way as the quadratic ones. I'm going to first change the f of x to be y equals, bring down my 1/4 x minus 3. And then what I'm going to do is switch out my x and y. So same type of process. Instead of the square root this time, we're just going to have our number in front of the slope. So the first thing I'm going to do is add 3 to both sides. And that's going to look basically the same between the linear and quadratic ones. So I have x plus 3 equals, and instead of writing this as 1/4 y, I'm going to write it as y over 4. It means the exact same thing, but it might make this step a little bit more clear. So I'd switched out the x and y, added my 3, and now all I did was take my 1/4 y and I expressed it as y over 4. Now since the y is being divided by 4 and I want to isolate the y, I'm going to multiply both sides by 4. And what that's going to do is get the y by itself on my right hand side. And on my left side, I'm multiplying the whole x plus 3 part by 4. So I threw that in parentheses. And what I'm going to do next is distribute and get 4x plus 12. And that is equal to y. And then lastly, I'm going to write this as f inverse of x, which is equal to 4x plus 12. And one of the things you can notice then is that my inverse function has a reciprocal slope. So since this slope was 1 over 4, this slope would be the reciprocal, which is 4 over 1, or just 4. And if I really went back to my part C from before, and notice I had y equals 4x plus 12, we can look at this red line, which has a slope of 4, so 4 over 1, my rise over run. And if I kept this going, I would see it hit my y-axis all the way up here, and that would be at 12. And that's why the equation then came out to 4x plus 12. So my verification algebraically would be using composition by taking f of f inverse of x. So same thing as I've done with the last two. I'm going to take my inverse function and substitute it in for x in my original function. So 1/4, and then in for the x, I'm going to substitute my inverse, which is 4x plus 12, and then start canceling. So the first thing is if I distribute my 1/4 through, 1/4 of 4 is just 1. So I have 1/4 times 4x, which is x. A fourth of 12 is the same thing as 12 divided by 4, which is 3. And then I'm going to bring down this minus 3. Same thing as before, I have my positive 3 and my negative 3, which will cancel, and I will be left with x. So that's what we wanted, is for my composition to come out as just x, which means that my functions cancel each other out. And the last problem, we had this one written before in slope-intercept form. What we ended up with then was to subtract the 2x on both sides, and I ended up with y equals negative 2/3 x minus 2. So this was our equation before. So what I'm going to do is the same thing, switch my x's and y's, and start this off the same way. So I'm going to add 2 to both sides first, and that's going to move this 2 over. And I'm going to rewrite this just like I did the last one as negative 2y over 3. So I'm kind of breaking this up into a couple pieces. And the first thing I'm going to do is bring my 3 over to the other side, and I'm going to do that by multiplying. So I have 3 times x plus 2 is equal to negative 2y. And what I'm going to do is distribute that left-hand side, and I'm going to do that up here. So if I take my 3 and distribute, I'm going to end up with 3x plus 6 equals negative 2y. And then what I would want to do is to isolate the y, divide both sides by negative 2. So I'm going to end up with negative 3 over 2x minus 3 equals y. And then if I write this as an inverse in function notation, I would say f inverse of x equals negative 3/2 x minus 3. So just going back to the idea that, again, this original function had a slope of negative 2/3, and my reciprocal has an inverse of negative 3/2. So just flipping the fraction, not changing it from a negative to a positive, but really just only flipping your numerator and denominator. So I'll do the composition, So that's my f of f inverse of x. So taking this function and substituting it back into my original. So I had, if I go right back into my original, I can take negative 2/3 times this fraction, which is negative 3/2 x minus 3, and then subtract the 2. So if I go through this, first thing that's going to happen by distributing this, these fractions are going to cancel each other out since I have negative 3 on top and negative 3 on the bottom, and same thing with the 2's, and it's a negative times a negative. So that's going to be a positive. And then I'm going to take this negative 2/3 and multiply it by this negative 3. So if I take my negative 2 times negative 3, I'm going to get positive 6, and my denominator of a 3 would come right over. And then I'm going to bring down this minus 2. So if I took my negative 2/3 times 3, I'm going to get this 6/3 value, which we know that 6/3 is really just 2. So then at the very end of this, I'm going to end up with the x plus 2 minus 2, which one more time is just x. So the inverses check out since I'm just left with x as my composition value, which means that the functions definitely cancel each other out. So quick recap of all this: we graphed quadratic functions and their inverses using table of values. I did my linear equations by identifying the slope, y-intercept, and some points, and just basically flip-flopping the x and y coordinates. And then we found the inverses of functions and verified them using composition, and did that both for linear and quadratic.